Hey guys, in this video I'm going to talk about an example in the book and how we can extend that example to discuss friction as well. This is a nice example because it shows that you can answer some pretty complicated questions by using the work energy theorem instead of doing the force acceleration thing. So here's the setup. We have a ramp of length L, goes up a height h, and there's an angle with respect to the ground, theta here. And you have a crate of some kind, and you want to push the crate up the ramp. And the question is, can you make the length of the ramp longer such that the work it takes to get the crate up the ramp is smaller? So this is a pretty natural idea because if you increase the length of the ramp, the angle of the ramp will be much less, and it certainly seems like it would be easier to push the crate up the ramp. But the question is that true? Is there really less work required to get the crate up the ramp if the ramp is longer? Well, the book gives you the solution, but I'll just run through it real quick. We're going to start with the work energy theorem right there. And the first thing to notice is that we have V equals constant. So we're pushing the crate up the ramp with a constant velocity. So that means that the change in kinetic energy is zero. The initial and final velocities are the same, so there's no change in kinetic energy. So kinetic energy is zero. Therefore, the total external work is zero. But the external work is made up of two different components: the work due to gravity and the work due to the push. This is the work that it takes me to push the crate up the ramp. That's the thing we want to see if it gets smaller. Well, so the book tells you how to rewrite these in terms of the variables in the problem. The work due to gravity is negative mgl sine theta. It's negative because the work of gravity is preventing you from moving the block up the ramp. And then mgl sine theta, the sine theta just is because of the trigonometry of the problem. As you go up the ramp, there's an effect, which means that the gravity is actually pulling downwards a little bit. This wouldn't be true if you were pushing it straight along the ground. So this thing is equal to zero, and so that tells us that the work required to push the crate up the ramp is mgl sine theta, and actually, because L sine theta is h, this is just mgh, and at some point we're going to learn that this is the potential energy due to gravity. But the important thing is that h is the only thing that shows up here, L does not. So the length of the ramp does not matter. The only thing that matters is the height of the ramp. And so a couple of things that we want to notice from this question. The first thing is that the work energy equation right here is a scalar equation. So that means, let's box this guy in too, that these are just numbers. This is the number, this is the number. This is not like Newton's second law when you study forces, and that is a vector equation with two components. This is a scalar equation. That's because energy itself, the concept of energy, is a scalar. It does not have a direction. It just is a notion of how energetic a system is. A spring or some thermodynamic system or a bouncy ball or something like that. That's intuitively a quantity which is intrinsic to the object or intrinsic to the system. It doesn't have direction, so it's a scalar. That's great because scalars are hard, because vectors are harder than scalars. It doesn't mean that you totally get out of doing trig because, right here we had a trig thing going on right here so we could get the height of the object. But one of the things which makes energy more convenient is that you don't need to worry about the direction. It is a scalar equation. The second thing to notice about this is that we can easily add friction to this consideration. So it's very natural to say, oh, okay, well, the length of the ramp didn't matter, but what if there's friction? Then if there's friction, then the ramp is going to be very long. The longer the ramp is, the more friction is going to push on it because you're going to have to be pushing against friction that entire way. And so we'd like to say, well, what does the answer change if we add friction? And because we're doing work energy, this is a very simple question to answer. Okay, so what about friction? We're going to start by writing down the work energy equation. As in the first case, the change in kinetic energy is zero because the velocity isn't changing. And the external work is due to three different sources: the work due to gravity, the work due to me pushing up the ramp, and the work due to friction, which is working against me pushing up the ramp. Those all add up to be zero. So nothing about gravity is changing in this case, so the work due to gravity is mgl sine theta, same thing as negative mgh. But what is the work due to friction? We don't know what that is, so we're going to have to work a little bit to get it. Okay, so I'm going to write down the work due to friction. The negative sign is there because the force of friction is in the opposite direction as the movement of the block, so that's a negative sign. And the distance it travels is up the ramp, L. The definition of the force of friction is mu Fn. Just a cautionary note, A lot of people I see are still writing that the force of friction is mu. That is not the force of friction. Mu is the coefficient of friction. It's the ratio between the force of friction and the normal force. It has no units. It cannot be the force of friction. I'm going to start really getting people for this, and on exams I'm thinking about just marking problems entirely incorrect if people start writing the force of friction is equal to mu, because not only is it incorrect, but it's conceptually wrong. Mu tells you the ratio between the normal force, which is somehow related to how heavy the object is in many cases, and the frictional force. So please stop doing that. Anyway, we need to find the normal force. So in this case, we can't totally get away from Newton's second law. In order to find the normal force, we're going to need a free body diagram. We're going to need to find Newton's second law. So let me draw a free body diagram. Okay, here we go. So I don't think we've talked very much about this, but the coordinate system I'm going to pick is going to be tilted. This is the y direction, this is the x direction. It's pretty obvious why I'm doing that. Most of the forces are actually lying in the plane of the ramp and off the plane of the ramp in these two directions. And so I'm picking my coordinate system in exactly that way to try to take advantage of that. So I need to write Newton's second law, which says that the normal force is the sum of the normal force and the gravitational force in the y direction is going to be equal to 0 because the thing is not accelerating. That's my angle. So the gravitational force in the y direction is mg cosine theta, and that tells me exactly what my normal force is. Okay, so I want to put that over into my force of friction equation, and I can just stick that straight into here to figure out what the work due to friction is. Mu mg L cosine theta, and notice that we can do a similar thing that we did up here when we wrote L sine theta is h. L cosine theta is going to be d, that is going to be that d right there. So we can just write this as negative mu mg times d. Okay, so now putting all this stuff together, I can solve for WP because I have negative mgh is the work due to gravity, negative mu mgd is the work due to friction, and so I can finally solve for the work that is required for me to push this up the ramp at a constant velocity. mg times the quantity h plus mu d. So I just did some rearranging and some algebra. None of that is too important. You can sort of see right here, this part mu d mg, this is the work due to friction, and this mgh right here, that's the work due to gravity. Now let me put a box around that. Bam. Okay, so now what about our question? Can we decrease the amount of work it takes to get the crate up the ramp by increasing L? And the answer, unlike the first case, is no. Because we have the work due to gravity, mgh, but we also have this additional part which depends on the coefficient of friction and the d here, which is the distance along the bottom. So if we had increased L out to here, d would get bigger and it would require more work to push the thing up the ramp. So in fact, this the result from the book fails when you add friction into the problem. Another thing that I'd like you to notice is that there's this combination right here, h plus mu d. So that is the height of the ramp, the distance of the ramp, and mu is multiplied by one of the two. This is a very common kind of expression that you see in these problems where you have blocks and on ramps that have friction. You might see it in a slightly different form. The most common one is this. This I've just written h as L sine theta and d is L cosine theta, so I've done the opposite that we did here, right there, and there. This is more common, but this is the kind of thing that when you come across a block problem, you should look for these kinds of terms. Because these kind of terms look a little bit strange, but they are extremely common when doing block problems on ramps. Okay, so I think that's all the lessons I have for this. I'll see you guys in class. Thanks, guys.